All right, so the first thing that we're going to be reviewing is linear functions, just because I'm assuming that you are pretty good at these and that you remember it and all of that you can work with them. So linear functions come in three forms. Two of them you're probably familiar with. One might be kind of new to you. So the first one is standard form. That's ax plus by equals c. The next one is the one that is probably new, and that's point slope form. It is not typically used in lower levels of math, but it is used all the time in calculus, and it's fairly easy to work with, which is why I'm not worried about introducing it quickly. So you have y minus y sub 1 equals m times x minus x sub 1, and it's called point slope form because your x sub 1 and your y sub 1 are a point that they would be giving to you, and then the m is the slope. So you literally just plug them in and you're done. The next one is the one you're probably the most familiar with, which is slope-intercept. And that is y equals mx plus b. And it's called slope-intercept because they give you the slope and the y-intercept for the equation. And then last, we'll probably need to remember that to find the slope, we need to have 2 points, and so that would be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. You might have also seen it as delta y over delta x, so the change in the y's divided by the change in the x's. And just to remember, the first point would be x1, y1, the second point would be x2, y2, and so that's where that notation comes from. So the first thing we're going to do is just remember how to graph all of these. So hopefully you have some graph paper. So the first one that we're going to graph is y equals 1/2 x plus 3. So this would be slope-intercept form. And typically on a graph, if you label your boxes as anything other than 1, then you should write the numbers in. And we're just going to go by 1, so we'll say that it's okay the way it looks right now. So since this is in slope-intercept form, the y-intercept is 3. So I'll draw the y-intercept at 3. And then this is telling me that the y is changing by 1 and the x is changing by 2. So it's going to go up 1, right 2, up 1, right 2. All right, so we're going to keep that. Now, I'm going to convert this to standard form because sometimes you have to do that, and I find students are not as great with that. So we're going to keep the y equals 1/2 x plus 3. Now, to get this in standard form, I need the x to be on the other side because in standard form the x and the y are together. So that would give me negative 1/2 x plus y equals 3. So I just subtracted it over. And then in standard form, typically we want the leading term, the x term, to be positive, and we don't want it to be a fraction. So what I'm going to do next is I'm going to take this entire equation and I'm going to multiply it by negative 2. And the reason I'm going to do that is because it's going to force that x to become positive, and it's going to make it so that it's not a fraction anymore. So negative 2 times negative 1/2 x is just positive x. Negative 2 times positive y is negative 2y. Negative 2 times 3 is negative 6. So that would be the standard form of that specific equation. Now, sometimes in standard form they'll ask you to graph, and some students find it most comfortable to solve for y and get it in this form so they can graph it. But there's actually an easier way if you want to just leave it in this form, and we call it the cover-up method. So if you think about the way that your x-intercept and your y-intercept work, is that an x-intercept, I'm going to draw a little sketch off to the side here. An x-intercept would be along the x-axis, and the y value at that point is always going to be 0. So you're always going to have a number for x and a 0 for y. And if you think about how it works when you plug in 0 here and you do 2 times 0, that's just going to be nothing, no matter what that coefficient is. So the x-intercept here is negative 6. So you have the point negative 6, 0. And then a y-intercept would be on the y-axis, and so the x value there would be 0. And so we're going to do the same thing. If I plug a 0 in there, then it would be gone, so I'm just going to cover that up. So I'm solving the equation negative 2y equals negative 6, and that means that my y value is just plain old 3. So if I look back at my graph, I could have graphed this by saying that my y-intercept is 3, and then I could have gone over to negative 6 on my x-axis and drawn a point there and connected them, and I would be done. So if you are given an equation in standard form, you can graph those from there. Now point-slope form is kind of interesting because there's lots of different points you could use if you wanted to write the equation for that. So I could write an equation from this point, or this point, or this point, and they would all look a little bit different. So if I use the point, we've got 2, 4. If I have the point 2, 4, and I write an equation for that, then I would have y minus 4 equals the slope, which was 1/2, and then x minus 2. And that is an equation that works in point-slope form. Or I could go over here, negative 2, positive 2, and I would have y minus 2 equals 1/2, and then x minus negative 2 would be x plus 2. And that would be another equation that is equally accurate. So you have some options there. Alright, so that's all the review that I'm going to do on linear functions. I also wanted to talk about parent functions and transformations. So that's going to be our next heading. Alright, so a parent function is something like y equals x squared, which is a parabola, or y equals the absolute value of x, which would be an absolute value graph, or you could say y equals the third root of x, which would be a cube root graph. So those are parent functions, just kind of the standard. And so we have those parent functions, and if you guys recall, we also have transformations for those. And so if we look, a typical one that students look at, and I'm just writing this in function notation, but it really means the same thing as y. I'm going to look at a parabola first, just because that's where I don't know, I feel like we work with parabolas or quadratics most often. So we have, these are the different transformations. So you typically have a variable or a coefficient here, and then a number here, and a number here. But you don't always have to have it looking the same. So we might also have a transformed graph that looks like a square root x minus h plus k. Or we could have, if we were going to do a log graph, the log would have a base of b, so that would be some specific number. So you'll find that no matter what the parent graph is that you're looking at, the coefficient in the front is what we refer to as a, and then the part that's inside of the graph, you'll notice all these seem to be inside. Those are the h specifically, and then the k is always on the end. So if you recall from your previous math classes, if we're looking at a and what those transformations would be, then we're going to say if the absolute value of a, it doesn't matter if it's positive or negative, if the absolute value of a is less than 1, then this is a vertical compression. Some people say shrink. It has the effect of making the graph look fat. If the absolute value of a is greater than 1, then we would say this is a vertical stretch. It makes the graph look skinny, makes it taller and skinnier. And then if it's negative, then it means that it reflected over the x-axis. All right, this part right here, the minus h, it moves the graph to the left and to the right. And it's always the opposite of what you would think. So the type of number that moves it to the left is actually positive numbers. The type of number that moves it to the right is actually negative numbers. And then the plus k on the end is moving up and down. Negative would be moving you down, positive would move the graph up. So that's exactly what you would think. Alright, so we're going to get our graph paper out again and look at a specific example of this. So I'm going to say f of x equals 3 times x plus 1 to the third minus 2. And since in front of this we have a 3, I know that this graph is going to be 3 times as tall as one of these graphs would normally be. So I'm going to give myself a little bit of space here. And I also know it's going to be moving to the left and moving down. So this would be left 1 and down 2. So I guess I'll give myself some space going down. Alright, so if I write these transformations, the 3 tells me that it's a vertical stretch of 3. And to be mathematically correct, you would say a vertical stretch by a factor of 3, because you'd be multiplying by 3. This means left 1, and then this is down 2. So just so I can show you guys, there we go, how this would work from the original graph, I'm going to go ahead and graph this part. Some people have these memorized. I had to memorize them when I was in school, but we don't typically make you guys do that anymore. So the original parent graph is a cubic, so it's x to the third, and so I went ahead and typed in x to the third, and then I'm looking at the graph, so it's going to be this general shape, but we're going to move it. So I'm going to go ahead and look at my table of values here. So the original graph is going to start at 0, 0, so I'm going to go ahead and take that original point, and I'm going to go left 1 and down 2.